Hey everyone, calling all engineering students. If you are gearing up for your Mathematics 1 exam, you are in exactly the right place. Think of today's explainer as your ultimate structured study guide for completely demystifying complex numbers. We're going to break down both Cartesian and polar forms, figure out how to switch between them without breaking the sweat, and give you the exact strategies you need to tackle these problems on test day. Let's get into it. So let's kick things off with a seemingly simple question. How do you solve an equation when the real number line literally just runs out of room? Picture the equation x squared equals -1. If you only have the standard real numbers to work with, well, you're totally stuck. You can't square a real number and get a negative result. No way. Real numbers alone just aren't enough to solve every equation. To break through that wall, we have to expand our thinking into a completely new dimension. Here's our quick roadmap for this explainer. First, we'll go beyond the number line. Then, we'll explore the Gaussian complex plane. Third, polar form and Euler's formula. Fourth, how to convert Cartesian to polar. And finally, mastering complex number operations. All right, part 1, beyond the number line. To break past the strict limitations of that one-dimensional real number line, we need to introduce one absolutely vital rule. Enter the imaginary unit, denoted by the little letter I. It's defined by a single property. I squared equals -1. And really, that's it. As your lecture notes probably hammer home, calculating with complex numbers follows the exact same rules as standard algebra. The only trick? Whenever you spot an I squared, you swap it out for a -1. This tiny, elegant addition is the foundation for everything we're about to do. Moving right along to part 2, the Gaussian complex plane. Now, doing the algebra is great, but let's be honest, as engineers, we need to see things. And what's surprisingly intuitive here is how a complex number becomes so concrete once you map it out. Take the complex number z equals a plus b times I. Instead of just plopping a single dot on a 1D line, we now plot a point on a 2D grid, the Gaussian complex plane, or the Gaussian as it's called in your materials. Your A value, that sits on the horizontal axis, the real axis or real tile, and your B value sits on the vertical axis, the imaginary axis or imaginaire tile. The key takeaway here is that both A and B are just standard, everyday real numbers acting exactly like your typical X and Y coordinates in this new 2D landscape. Next up, part 3, polar form and Euler. Normally, we navigate a graph by walking left or right and then walking up or down. But what if we change the rules? What if you stand at the origin, point yourself in a specific direction, and just walk a set distance? It's like a new coordinate life hack. We can link this Cartesian form to the new polar form using a basic right-angled triangle. The straight line distance from the origin out to our point z is our magnitude, r, or the betrog. Then, the angle formed starting from the positive real axis, sweeping counterclockwise up to that line, is our argument, phi. Basic trigonometry tells us the real part, a, is just r times the cosine of phi, and the imaginary part, b, is r times the sine of phi. Boom! We just swapped our standard x and y coordinates for a pure distance and an angle. And that realization leads us straight to Euler's formula. Oh man, this is a real game changer. It's this majestic, incredibly compact way to express our polar geometry mathematically. Instead of writing out clunky sines and cosines every time, we just write our complex number z as r times e to the power of I times phi. It effortlessly packs both the magnitude and the direction into one brilliant little exponential package. And trust me, this isn't just some neat math trick to show off. As we'll see in a second, it makes complex calculations vastly easier. Okay, part 4, converting Cartesian to polar. Theory is fun and all, but you need to know how to actually execute this on your exam. So I highly recommend breaking the conversion down into a bulletproof 2-step checklist. Step 1, find the betrog, the magnitude r. You do this using the good old Pythagorean theorem. R equals the square root of a squared plus b squared. Step 2, find the argument, the angle phi. Now listen up because this is absolutely crucial for the exam. You have to double check which quadrant your point is in. Your lecture notes define phi between -pi and positive pi. The specific formula you use to find that angle depends entirely on whether your imaginary part b is positive or negative. Do not skip checking that. Let's actually walk through a concrete exam problem straight from the source materials to see this in action. Say we need to convert z equals 1 minus the square root of 3 times I into polar form. Okay, our a is 1 and our b is -square root of 3. Step 1, the magnitude r. We take the square root of 1 squared plus -√3 squared. That simplifies to the square root of 1 plus 3, which is the square root of 4, so our r is exactly 2. Easy. Step 2, the angle phi. Because our b is negative, it's below the real axis, the lecture notes tell us to use the formula, negative arc cosine of a divided by r. So we calculate the negative arc cosine of 1/2. The arc cosine of a half is pi over 3, making our angle phi negative pi over 3. Bring it all together with Euler's formula, and our final answer is 2 times e to the power of negative I times pi over 3. When you visualize this point, it makes total sense. It's sitting perfectly down there in the fourth quadrant. It's a simple, structured process that won't let you down on test day. Finally, Part 5, Mastering Complex Number Operations. So now that you can switch fluently between the two formats, we need to answer the big so what. Why do we even bother with two different forms, and when exactly should you use them when the clock is ticking during a high-pressure exam? Well, here is your ultimate cheat code. Burn this into your memory. The Cartesian form, the a plus bi, is absolutely the best tool for addition and subtraction. You literally just add the real parts together and add the imaginary parts together. Done. On the flip side, the polar form, r times e to the I phi, is the undisputed heavyweight champion for multiplication, division, and finding roots. If you try to multiply complex numbers in Cartesian form, you're stuck expanding brackets and constantly reminding yourself that I squared is -1. Polar form makes it almost completely effortless. Let me show you exactly why. The geometric beauty of multiplying in polar form is amazing. When you multiply two complex numbers this way, you only do two super basic things. First, you multiply the magnitudes together, so r1 times r2. You're literally just scaling the length of the line. Second, you just add the angles, the arguments together, phi1 plus phi2. Geometrically, you're just rotating the point around the origin. And division? Same thing, just in reverse. Divide the magnitudes and subtract the angles. It is a massive, massive time saver for your exam. I want to end today's explainer with a provocative thought that perfectly ties the whole shebang together. If you hit Euler's formula, set the angle phi exactly to pi, and the magnitude to 1, you end up at the Cartesian coordinate of -1. Shuffle that equation around, and you get Euler's identity, e to the power of I times pi plus 1 equals 0. It's widely considered the most beautiful equation in mathematics because it perfectly proves that Cartesian form, our 1 and 0, and polar form, our e and pi, are literally just two sides of the exact same coin. So as you walk into that exam room, just remember the golden rule: Cartesian for adding, polar for multiplying. Keep that elegant structure in mind, and you are going to absolutely crush it. What other mathematical mysteries are waiting to be unlocked with tools like this? That's a question for another day. Thanks for learning